All right, here today we have ourselves another differential equation, ladies and gentlemen, boys and girls. This time, this differential equation is not separable. We can get x's all on one side and y's all on one side, but they're not all in one term. So the y's aren't in one term. We have just a y prime and a y term. So we need to use a different approach here. Besides using the method of separation of variables, probably the most simple method is the method of the integrating factor. And in this video, I'll just go ahead and give you a quick example of how the integrating factor works. And maybe in a couple more videos, I'll explain why it works. And I'll prove that it works. Here, let's go ahead and just do an example. So we got this equation here. We got y prime minus y equals 2x e to the 2x. It looks pretty wicked. It looks like, how are we going to solve this? We have a 2x times e to the 2x. That just looks wicked. All right, so what we need to do is get something called the integrating factor. The integrating factor only works when we have an equation of the form y prime plus p of x y is equal to q of x. If we look at these terms up here, we notice that p of x is equal to -1 and q of x is equal to this, well, the 2x e to the 2x. So we do have in the correct form we want. But once we have in this form, what do we need to do? Well, we need to go ahead and create what's called the integrating factor here. The integrating factor can be created, we can get the integrating factor, we'll call it mu. Mu is the standard variable used for that, not mu of t, mu of x here. Mu of x is equal to e, and that's the natural e, the e that you know, the e that everyone knows and loves, e to the negative, well, not negative, sorry, e to the px dx. So what did I say earlier? Well, it's going to be in the form y prime plus p of xy is equal to q of x. So here p of x is actually just -1. It's going to be -1 times dx. So this is our integrating factor. Once we get our integrating factor, we can go ahead and, well, do the integration here. So the integral of -1 dx is, well, that's just negative x, right? So our integrating factor is going to be mu of x is equal to e to the negative x. Pretty simple integrating factor so far. Once again, this is just an example of how this method's used. We'll see how it's used to actually solve this differential equation. So what can we do? We can multiply this whole equation up here through by the integrating factor. What are we going to get? We're going to get e to the negative x, y prime, minus e to the negative x, y, is equal to, well, what do we have here? I think it's going to, one of those e to the x's are going to cancel out. It's just going to be 2x e to the x, correct? Yep, I think that's correct. So now what do we have here? And this is the magic of the integrating factor. What we'll notice here is this is actually just using, if you can kind of do the reverse product rule. If you notice, this is actually just the derivative of the term y e to the negative x. Now, is that true? Well, let me go ahead and just do the derivative right now. So the derivative of y e to the negative x is, well, it's going to be y e to the negative x times -1. And it's going to be plus y prime e to the negative x. And we can rewrite this as e to the negative x y prime minus e to the negative x y. Okay, so that shows that what we really have here, I was just showing you that this actually works out the way we want it to work. Okay, so what we actually have here is the derivative with respect to x of y e to the negative x. So if we use this method of integrating factor, we're always going to have the derivative with respect to x of y times the integrating factor. That's just the magic of how this works. And like I said, later on, I'll show you why it works this way. Okay, so we're almost done. Now we're going to say this is equal to 2x e to the x. And now we're at a point where we can just do some integration on both sides. So if we integrate with respect to x on the left, well, this d dx is just going to go away. So then we're going to get y e to the negative x is equal to integral of 2x e to the x. So we'll have to do a little bit of integration by parts, and nobody likes doing integration by parts, I understand. So we're going to have, I think, u is equal to 2x, dv is equal to e to the x dx. So du is equal to 2 dx, and v is equal to e to the x. So what we're going to get is that in the end, when we do some in the end, after we do some integration by parts, we're going to get y e to the negative x. And remember, the integration by parts formula is integral of u dv is equal to uv minus integral of v du. So we're going to get 2x e to the x. Then we're going to get minus the integral of v du. And that's just going to be actually v du in this case. So it's just going to be 2 e to the x. And we're going to have a constant here. So we're almost done. Just one more step. We're just going to get this in terms of y. So finally, we're just going to multiply we're going to multiply through by e to the x to get rid of this e to the negative x over here. So we're going to have y of x is equal to 2x e to the 2x minus 2 e to the 2x plus c e to the x. So that is our final answer. And this is the method of using the integrating factor.